This is Zener diode characteristics. In this experiment, we are going to calculate the new voltage in forward bias, breakdown voltage in reverse bias. See, this is a power source. Just we need to connect the source to circuit. Next, this is a Zener diode. This is a Zener diode. This black line gives N type and this is P type. Here, this is negative terminal, this is positive terminal. We are going to connect this N type to the negative terminal. So that means that this is connected in forward bias. Next you see here, it's a milliammeter. There is a ammeter and connect this ammeter in this place. Negative terminal to negative terminal, positive terminal to positive terminal, and here positive, here positive. This is voltmeter. So this is connection is done. So now we are going to find out what's the new voltage in forward bias. For that, we need to increase voltage across this diode, and what is the current is obtained that we are going to see now. So this, so I'm going to increase voltage of Zener diode. To say initially 0.1, and what is the current is obtained and 0, and 0.2, what's the current obtained 0, 0.3, what's the current obtained 0, 0.4, current obtained is 0, and 0.5, the current obtained is 0. So because of here, when we have discussed regarding this PN junction forward bias, there is a depletion layer which provides negative potential. So whatever voltage is given to this, that negative potential opposes this. So that's why we want to know it offers less resistance. So that's why we won't get any current till certain value of voltage. Increase this voltage slowly, and you say 0.6. You say 0.6, we didn't get any current. You increase to 0.66 or 0.67. 0.66, you see we got 0.1 milliamp current, right? And you increase the voltage slowly and find out how much current is obtained. And note down this given voltage and current obtained in this tabular column. Slowly you increase voltage till 0.8. You see how much current is obtained over here. And plot a graph between voltage and current. You will get a curve like this. Here this is current, this is voltage. We will get a curve like this. And if you draw the tangent to that curve, it meets voltage axis at certain value. That value we call it as a new voltage. So this is forward bias. Next we will go for reverse bias. Just to minimize all the voltages and switch it off and interchange this diode and plug it back. Switch it on. Now repeat the same procedure how we have done for the forward bias. Increase this voltage. You say 0.1 or 0.2, 0.3 and 1, 2. See, there are two tabs. One is for small increment of voltage and this is high increment. So here if you use this, we can increase voltage across this Zener diode, 1 volt, 2 volts, 3 volts, 4 volts. So 3 volt, 1 volt, 2 volts, 3 volts, and 4 volts, 5 volts, and 6 volts, 7 volts, 8, 9, 10, 11. So till 11.65 we are not getting any current, and 11.7 also we are not getting current. You know what is the reason? So in reverse bias, so it offers more resistance, and once it reaches to certain voltage, the current will increase rapidly, exponentially. So till 11.7 we didn't get any value. For 11.72 we are getting 0.4. We just increase 0.7, increase to 11.74. See, it is reached to 1.9. So if you keep on increasing these voltages, so there is exponential growth in current, right? That can be observed if you plot a graph between voltage and current in tabular column. If you plot a graph between voltage and current, initially we won't get any current till 11. So once it is reached to certain voltage, the current exponentially increases. If we draw the line to that curve, it meets voltage axis at certain voltage. That voltage we call it as a breakdown voltage, or you can call it as a Zener voltage. Based on this property, this Zener diode has been used as a voltage regulator.